All right, folks, we are moving on to talking a little bit more about integration. So remember that the integral is area under a curve. We're trying to calculate or find a good way to calculate that area under the curve. And Riemann was this dude who came up with this idea of breaking that area into rectangles because it's easy to figure out the area of a rectangle. Now you'll notice, here's an example. Here's that same curve. This is the x squared curve again. And this time they've taken the interval. Remember, we broke it into 4 subintervals, and that gave us an estimate. And then in this case, they decided to break it into 10 subintervals. Now remember, the actual area underneath the curve was 1/3. And so as you look, they took the area under the curve, they broke it in, or this space, they broke it into rectangles. They made 10 rectangles. They calculated the area. They got 0.385. Then they decided to break that. Instead of using 10, they used more, and it got us to 0.38 or 0.35. Sorry, this was 0.385. This one, 0.35. Now they did it for 50. They took that, instead of making it into 4 intervals, they made it into 50 intervals. And you can see, like, look at all the error here, right? This is an overestimate big time. And then the overestimate gets a little bit less. The overestimate gets a little bit less. And then Corby decided to make a little chart here of a left endpoint estimate and then a right endpoint estimate with breaking the interval into a certain number of intervals, I guess, subintervals. So as you get closer and closer, the more that we could, the more intervals that we look at, the closer our value gets to the actual value of 0.3 repeating, which was the area of the curve there. So you could theoretically, you could imagine, as mathematicians often do, is we could imagine as n approaches infinity, what would that area end up being? If we could do infinitely many little rectangles underneath there, we would get exactly that area under the curve. So here's our boy Riemann. Oh, is it Bernhard? Bernhard? I can't remember. Right? I think I already said. Oh yeah, right there. Duh. There it is. Bernhard. My boy Leonhard Euler says that weird H in there, but whatever. All right. So he came up with this idea that, okay, what happens? I'm going to do is I'm going to take the sum. That's why we did the sum on the front page. We're going to take the sum of all these little areas. So that's what this is calculating. This is my function height. This is the interval. So this is the area formula. This right here is the function height. Function value, sorry. That's the function value, which equivalently becomes the height of our rectangle. This here is how far each interval is. The width of our interval is some small little delta x. Now, as we make n bigger and bigger and bigger and bigger, as we do this more and more often, in other words, if we make those have more and more and more rectangles, the closer we'll get. If we could do it infinitely many times, we would then get the exact area under the curve, which is what we call a definite integral. Remember, we did some integration in the last unit that they didn't have any numbers here. So that's what we call an indefinite integral. That's why you got to put plus c at the end. What we're going to do is we're going to evaluate these. We're going to get an actual number. That's like what we did up here, where you get the actual 1/3. All right, so let's do another estimate. We're going to approximate a little bit more using our sum method. So I want you to take and make a little sketch. Let's put the sketch. Yeah, there's plenty of room. Let's put the sketch over here. Please make a sketch. We're going from 1 to 9. So 1, 2, 3, 4, 5, 6, 7, 8, grown 9. All right. 1 to 9, and make a sketch of the square root function. I'll give you a second. Hopefully you know how to graph the square root function. Let's see how you did. All right, so our square root function we know looks something like this. We can get more specific than just randomly drawing a curve here. We can get some values in here. So we know that the function value of, when we plug in 0, 0 square rooted is 0, square root of 1 is 1, square root of 4 is 2, square root of 9 is 3. So we get a curve that looks something like that. We want to divide this into, our actual interval, though, is from 1 to 9. So we want to kind of block that section off. We're going from here to here. And we're supposed to divide this using 3 subintervals. So I need to take this gap, I need to divide it into 3 equal parts. So that's going to be 1, 2, 3, 4, 5, 6, 7, 8. All right, so we need to take this gap of 8 units and divide it into 3 equal sections. Thanks a lot, Corpy, for making us go from 1 to 9 instead of 0 to 9. So we could have easily made it into, you know what? Yeah, let's just do it. Let's change it, man. I don't want to. We're going to have all these crazy numbers. This way we should be able to actually get a nice answer. So let's go from 0 to 9. So this is the end of my interval from here to here. I'm going to scribble that guy out a little bit. All right, so I want to take this, I want to divide it into 3 equal subintervals. So at gaps of 9, that means each interval is going to be 3 units in length. So I'm going to label with a different color. Well, no, with black, I'll label 1, 2, 3, 4, 5, 6. So this is a gap of 3, this is a gap of 3, this is a gap of 3. We call those subintervals. 0 to 9 is the overall interval. These are called subintervals. All right, I'm going to let you try to do this on your own. See if you can come up with the formula again. So pause and give it a try. All right, let's see how you did. So I'm going to start off with the left side. So I go to my interval. I go to the left end. I track up to the function. That's my height. I track to the other end. So that's kind of a boring. I like that. It's easy. Then I go to 3. Oh boy, this isn't going to come out nice. Track up to the function. That's my function height. I go to the end of my interval. There's my next rectangle. I track up at 6. All right, it makes sense that these are a little bit lower because this is an increasing function. So my left interval, my left endpoint estimation should be below what it actually is. All right, so how big are my gaps? My intervals are a common length of 3. My first function value is 0. Now I'll write it out. F of 0 plus f of 3 plus f of 6. Now we can actually evaluate these. 3 times f of 0 is 0 plus f of 3 is root 3. Gross. 6 would be root 6. We can't clean this up either at all. So this would be 3 roots of 3 plus 3 roots of 6. I'll encourage you to pause, do a right side limit. All right, let's see how you did. Now I'm going to go to the right end of the interval. I'm going to track up, and then that's going to be my height of my rectangle. Go to the right end of the interval. I'm going to track up. That's going to be the height of my interval. Go to the right end, the height of my rectangle. Go to the right, track over. That's going to be the height. We already know the width is going to be 3. That makes sense. All those greens are above the actual curve, so this is going to give me an overestimate. Let's figure out what that overestimate is. So we still have gaps of 3. I'm now doing the function value at 3 plus the function value at 6 plus the function value at 9. Well, that one won't be too bad. So I now have 3 times the quantity. F of 3 is root 3, root 6, and then root 9, of course, which turns us back into a 3. So I like to put the constants out front. You don't have to. 9 root 3 root 3. Just as a quick reminder, this was so my left endpoint of an increasing will be under. This is an under estimate. This is an over estimate. Because we've got an increasing function, that's going to cause the left to be over, left to be under, right to be over. All right, trapezoids. Oh, well, I'll talk about that in a sec. So I'll pause, encourage you to try it on your own. All right, let's see how you did. So my trapezoid is the left end point connected to the right end point. That's just a triangle. Left end point, right end point, and I get a bunch of these trapezoids. So my heights, so I've got my 1/2. That's part of the formula. Times my heights, which are all 3, or you could call them bases if you want to. Times, and then I've got to do the calculation of, so this would be f of 0 plus f of 3 plus f of 3 plus f of 6 plus f of 6 plus f of 9. I really wish I would have used some different colors here, but each one of these, so this, that's the base 1 and base 2 of each one of the trapezoids. So we have 1/2 times 3 times f of 0 ends up being 0. I like that one. Plus, now look, you're going to add these together, so let's add them together right now. So f of 3 is root 3, so that's going to be 2 roots of 3. Plus f of 6, that's going to be a root 6, that's going to be another root 6, so that's 2 roots of 6. Plus f of 9, we already know is 3. Combine some not combine like terms, just distribute, I guess. So it's going to be 3/2 times 2, so that's 3 root 3 plus 3/2 of 2 is going to cancel again, so that's going to be 3 root 6 plus 3/2 times 3, that's going to become 9/2 or 4.5. Now I can't tell if this is an overestimate or an underestimate because I was just talking about how I like to put the constants out front. Annoying. All right, well, let's actually calculate the true area and see how close these were. So I'm going to go back. I like to do it with alpha f2. I think that's just quicker. So I'm going from 0 until 9. My function is square root of x. And then I'm going with, can you guys, I hope that you see that, dx. So the actual area under the curve is, this is your calculator way of saying 18. Let's see how close our estimates were. So 3 root 3 plus 3 root 6. Oof, that's an underestimate, all right. The next one was exactly the same, but they did a plus 9 at the end. That's an overestimate, all right. The next one was the same, except it was 9/2. Oh, that's pretty close, pretty close, pretty close. So the actual, I'm going to write these down for future reference. The actual area was 18. It's kind of interesting, isn't it? I want to double check that. Who knew that'd be such a nice result? I'll just do a zoom 6. We don't really need a nice window here. I'm going to calculate my integral from 0 to 9. Shazam, it even has that little goofiness at the end. I guess that makes sense. If we integrated this, right, what would this look like if we integrated it? So we do a rewrite early and often, that's 1/2. I would add 1 to the exponent and then divide by that. So add 1, 3/2 plus 1/2 plus 1 is 3/2. Then when I divide by 3/2, that ends up being a flip and multiply. Plug in 9, square root of 9 is 3. 3 cubed is 27. 27 divided by 3 is 9, times 2 is 18. Yeah, okay, there you go. I'll talk more about how to evaluate a definite integral, but I just wanted to check for myself. This ended up being approximately, I got to go back here, 12.544. This was approximately, I'm not supposed to use approximates here, am I? This was equal to 21.544. And this was our best estimate at 17.044. All right, let's see if you can do the same thing now with a much simpler graph. Yeah, give it a try. Pause, go get them. All right, let's see how you did. You should have made a sketch. So I'm going from 0 to 4, so I really only need this side. There's 4, I guess. This will be 2, that'll be 1, that'll be 0. How high do I have to reach? So 2 times 4 will be 8. So this will be 8. I'm going to be kind of lazy and just write a couple of those in there. So our sketch should look like, so 0, I'm graphing 2x basically. So that's going to 0. 1 would be 2, 2 would be 4, 3 would be 6, 4 would be 8. Here's my curve. My interval, though, that they want us to cover, we're going from 0 until 4. That's my interval. Now, what's nice about this, you can cut it into as many subintervals as you want, but this is a shape that you can just calculate the area of. If I look at this shaded region in here, that's a what? What shape is that? Yeah, it's a triangle. So we can just go ahead and do the area formula for a triangle. I'll give you a chance to write it down first. This is not going to be given to you. This is one you got to know. Area equals 1/2 base times height. 1/2, our base is 4. Our height is 8. That's 2, that's 16. So if you can figure it out quickly graphically, it might be worth it just to do it. I mean, I'm gonna calculate it real. I think it's probably quicker. Let's go here. 2x, graph it. I want to get the integral from 0 until 4. 16. Cool, math works.